in previous class I was teaching you about single stage transistor amplifier. Okay, so for a single stage transistor amplifier, how we can determine the voltage gain, current gain, power gain, input impedance, output impedance, all these quantities, how we can determine it. Okay, so in previous class we have seen how to represent the amplifier circuit, single stage transistor amplifier, how to represent it in AC model, or how we can represent its AC equivalent circuit. Okay, so we have seen all these in previous class. Now we can determine all these parameters. Today we will determine all these parameters. Okay, so the circuit diagram for a single stage amplifier circuit is like this. This is R1, R2, RE, and this is RC. It is connected to VCC. Okay, then this is VI. Okay, this is RL, and like this. So this is the circuit diagram of a single stage BJT amplifier. Okay, it is in common emitter mode, CE mode, because this emitter terminal is common. Okay, here, and this is emitter bypass capacitor CC2, and this is CC1. This CC1 and CC2, these are coupling capacitors, and this is emitter bypass capacitor. So we have seen in the previous class, we have seen its working. Okay, now in this class we will see how to calculate various parameters. Suppose voltage gain, current gain, power gain, input impedance and output impedance of this complete circuit. How we can determine it? So in order to determine all these values, we have to analyze this circuit from AC point of view. Okay, so we can represent its AC equivalent circuit. Okay, so how we can represent its AC equivalent circuit? We can represent AC equivalent circuit how? Okay, so capacitors, all the capacitors has to be sorted. Okay, and this DC voltage source, here DC voltage source is only VCC, so we have to replace this with ground, that is VCC, it will be equal to 0. Okay, and so in previous class we have seen. Okay, but we have to represent this also BJT transistor with its AC equivalent. So we can represent BJT with its AC equivalent model. Okay, so one popular model is H parameter model. So by using H parameter model, we can represent this BJT transistor. Okay, in AC for analyzing this complete circuit. Okay, so first of all we will study about H parameter model. So what is this H parameter model? H parameter model, it is also known as hybrid parameter. H stands for hybrid parameter model. Okay, so a transistor, it is a 3-terminal device. A transistor, it is a 3-terminal device. Okay, Suppose this is terminal 1, this is terminal 2 and this is terminal 3. Okay. So a transistor, if it is a 3-terminal device, so we can make one terminal common to both input and to the output. So these are terminal 1, 2 and 3. Okay. So this is input port and this is output port. So a transistor, it is a 3-terminal device and it is a 2-port device. 2-port, how it behaves as a 2-port device? By making one terminal common to both input and to this output. So this is input side and this is output side. Okay. So suppose V1 it is plus minus, it is the input voltage, and say I1 it is the input current. Similarly I2 and V2, these are the output currents and output voltage. How we can represent these V1, I1, V2 and I2? How we can represent these 4 quantities? Okay. So in BJT transistor, we can represent these 4 quantities, or we can relate these 4 quantities by using these 2 equations. So you can write V1, it is equal to H11 into I1 plus H12 into V2. Clearly, how we can represent I2? It is equal to H21 into I1 plus H22 into V2. Okay, and in these parameters I1 and V2, these are independent. These are independent variables, and V1 and I2, these are dependent variables. Okay, so we can represent these 4 quantities V1, I1, V2, I2 by using these equations, these 2 equations. Okay. So from these 2 equations, how we can express H11? H11, it is equal to V1 divided by I1 when Vt is equal to 0. Okay. So what is this H11? H11 is V1 divided by I1. So this is input resistance or input impedance when V2 is 0. When V2 is 0 means with output sorted. So when output terminals means, suppose this is V2 and I2 is like this. So when output is sorted means these 2 terminals, suppose this is 2 and 2 dash, this is 1 dash, terminal 1, terminal 2 and terminal 3 for a BJT transistor. Okay, so if 2 and 2 dash both are sorted, then in that case V2 it is equal to 0. So V2 it is equal to 0 when output terminals are sorted. Okay, so it is the input resistance or input impedance. Okay. Then we can express H12, it is equal to, from this equation A, suppose this is equation A and this is equation B. From equation A we can get H12, it is equal to V1 divided by V2 when I1 it is equal to 0. So what does this mean? It is reverse voltage ratio. It is reverse voltage ratio with input open. So suppose when the input terminals are open, then in that case the current I1 it is equal to 0. So it is reverse voltage ratio with input open. Okay. Similarly, how we can represent H21? It is equal to I2 by I1 when V2 is equal to 0. Okay. So this is forward current ratio with output sorted. When the output terminals are sorted, then in that case V2 is equal to 0 and S21 it is equal to I2 by I1. S21 it is equal to I2 by I1 when V2 is equal to 0, means when the output terminals are sorted, then we can determine S21. Similarly, how we can determine H22? It is equal to I2 divided by V2 when I1 it is equal to 0. So this is output admittance or output conductance with input open. So S22 it is equal to I2 by V2. It is equal to S22 it is equal to I2 divided by V2 when I1 is equal to 0. When I1 is equal to 0. So with input open. Okay. So these are H11, H12, H21 and H22. These are the hybrid parameters. Okay. So these are hybrid parameters. Why these are hybrid parameters? Because see, H11 its unit is ohm. Okay. H12 it is unitless. H21 it is again unitless because current divided by current. This is voltage divided by voltage. It is unitless and its unit is I2 by V2. Its unit is mho or Siemens. Okay. So all these quantities have different units and some are unitless also. That is why it is known as hybrid parameter. Okay. BJT transistor, how we can represent these hybrid parameters? Okay. So H11 we can write it by Hi. H12 we can write it by HR. H21 we can write it by HF and H22 we can write it by HO. Okay. So for a common emitter mode BJT, for a common emitter mode BJT, common emitter mode BJT, okay, how we can represent H11, H12, H21 and H22, okay. So H11 it is represented by HI, H12 it can be represented by HR, H21 we can represent it by HF. Similarly, H22 we can represent it by HO. Okay. Now, when the transistor is in common emitter mode, then we have to write suffix E. And when the transistor is in, say, common collector or common base mode, then again for common collector we have to write IC. We have to put suffix C. For common base we have to suffix B, like this. So in this way, H parameters for common collector and common base can also be determined. So if we are determining these parameters for common emitter mode BJT, then also we can determine it for other configurations, that is common base and common collector. Okay, so we are saying for common emitter mode BJT. Okay, so if we are analyzing the amplifier circuit for common emitter mode, then we can analyze this circuit by the same technique for common collector and for common base mode. Okay. So how we can write these two equations for a BJT? So for a BJT, V1 for BJT which is in common emitter mode, V1 it is equal to, so we can write like this. Suppose this is base terminal, this is emitter terminal and this is collector terminal. Okay. Base terminal it is represented as 1 here, emitter terminal it is by 3 and this is suppose terminal 2. Okay, so it is VB and IB, it is BC and IC, like this. So the same equation for a BJT, how we can write? V1 it is equal to VB, it is equal to H11. H11 it is like this. We can write HIE I1. I1 is IB plus H12. It is HRE. B2. B2 is VC. Similarly, equation B we can write I2. I2 is IC. It is equal to H21. H21 it is HFE into I1. What is I1? I1 is IB plus H22 is HOE multiplied with B2. B2 is again VC. So suppose this is equation 1 and this is equation 2. Okay. So in this way we can represent a BJT transistor which is in common emitter mode. Common emitter mode means emitter terminal is common to both input and to this output. So it is behaving as a two-port device. Two-port means first port is input port, second port is output port. That is why it is two-port device and three terminals. Emitter, base, collector. These are the three terminals. And two ports are input port and output port. Okay, so this BJT, so we can represent the voltage VB, IB, VC, IC like this by using equation 1 and 2. Okay, so how we can represent these two equations? By using circuit. Okay, so suppose equation 1, how we can represent this by using circuit. This is VB, HIE, HREVC, HREVC. Okay, so this is hybrid input equivalent circuit. This is hybrid, this is the circuit representation of BJT, that is input equivalent circuit. For this equation we have represented it by using circuit. This is HIE and the current flowing is IB. Okay, so this equation it is represented like this. This is the input equivalent circuit. Similarly, output equivalent circuit, how we can represent it? It by using circuit, it is, this is HFE into IB 1 by HOE. Okay, this is collector terminal and this is emitter terminal. Similarly, here it is emitter terminal and the base terminal is, this is the base terminal. This is base terminal and this is hybrid output equivalent. This is the hybrid output equivalent representation of BJT. Okay, so the complete, how we can represent it in circuit form. We can combine these two. So after combining these two circuits, it will look like this. This is VB, HREVC, one by HOE, and this is HFE into IB. This is emitter terminal and this is base terminal and this is collector terminal. Okay, and suppose this is ground. Okay, so for a BJT, this is the equivalent BJT in H parameter model. So in AC model representation of BJT, we can represent it like this. Okay, so this is base terminal, this is emitter terminal and this is collector terminal. So we can represent the BJT with its S parameter model like this. Okay, so we will analyze the various parameters for this circuit. This is VCC and this is R1, this is R2, RE, this is RC, RL, this is coupling capacitor and this is emitter bypass capacitor and this is say VI. Okay, and all these are connected to ground. So how we can represent this amplifier circuit? This is single stage BJT transistor amplifier in common emitter mode configuration. So how we can represent its AC equivalent? Okay, so we can represent it like this. For AC equivalent, we have to sort the capacitors and we have to connect ground at the VCC. So all the DC voltage source has to be replaced with ground and the capacitors has to be sorted. Okay, so it will look like this. Okay, and see, this is RC and this is RL, this is R1 and this is R2, and this is emitter terminal, this is base terminal and this is collector terminal. So V output we are getting across this, and this is VI. So this is the AC equivalent of this circuit. Okay, but we have to represent this BJT again with its AC equivalent. Okay, so we can represent this BJT with AC equivalent means by using H parameter, model of BJT. Okay, then the complete circuit will be the AC equivalent circuit of this. Okay, so it will look like this. Okay, and like this it is HIE, this is R1, this is R2, this is HRE into BC, and here it is HFE into IB, and like this it is 1 by HOE. Okay, then RC and RL. Then it is RC and RL. Okay. Okay. So this is emitter terminal, this is base terminal, and this is collector terminal. So we have replaced the BJT by its H parameter model, and this is ground. Okay, so this is the representation of BJT in H parameter model. Okay, so from this circuit, how we can determine all the various quantities? Suppose current gain, voltage gain, power gain, input impedance and output impedance, how we can measure. Okay, so this is the complete circuit representation in AC model. So we have to approximate it. So by using approximation method, we can approximate this circuit. Okay, so how we can approximate the circuit? Suppose this is VI. Okay, this is plus minus. This is the input voltage source. So for an ideal voltage source, its internal resistance is very less. For ideal case, it is 0. Okay, so if we are considering this as a very good voltage source, then its internal resistance it is very less. So this R1 and R2, and this internal resistance, suppose this Ri is very less, so suppose this is for Ri, okay, so this is R1 and this is R2, all are in parallel. So for an ideal case this is 0, so the parallel combination it will be very less, okay. So the presence or absence of these two resistors will not affect the current IB, okay. So we can remove these R1 and R2 transistors, because for an ideal voltage source its internal resistance is very less. For an ideal case it is 0. So under this situation we can replace R1 and R2, okay. Then the typical values for all the hybrid parameters in case of BJT in common emitter mode, it is like this: HIE, it is equal to 1 kilo ohm. HRE, this is equal to 2.5 into 10 to the power minus 4. It is unitless. HFE, it is equal to 50. HFE, it is equal to beta, which is 50. And HOE, it is equal to 25 microsiemens. So 1 by HOE, 1 by HOE, it is approximately 40 kilo ohm. So these are the typical values of hybrid parameters in BJT, which is in common emitter mode configuration, okay. So from this we can see what is the value of HRE. HRE, it is 2.5 into 10 to the power minus 4. So this multiplied with VCC, it will be very less quantity. So we can neglect this also. So we can remove this, okay. Now 1 by HOE, its value, and now we can write RAC, it is equal to RC in parallel with RL, okay. And RAC, its typical value, it is 1 kilo ohm. These are the typical values. This is typical value for a BJT in common emitter mode. And for amplifier analysis RAC, this is the typical value, it is 1 kilo ohm, okay. Now just now we have seen that 1 by HOE, typical value of 1 by HOE, it is in the range of 40 kilo ohm. Now this 40 kilo ohm in parallel with 1 kilo ohm, so approximately it will be RAC only. So we can replace these 3 and it will be equal to RAC only, okay, and this is V out. So in this way we can approximate the circuit. This is the circuit representation of single stage amplifier circuit by using approximate analysis. Okay. Now how we can determine the current gain from this circuit? The current gain, it is equal to output current divided by input current. So output current is what? Output current is IC divided by input current is IB. Output current is HFE into IB divided by IB. So this is equal to HFE. So the current gain, it is equal to HFE. So we can write AI, it is equal to HFE, which is equal to beta of the transistor. Then voltage gain. Voltage gain is output voltage divided by input voltage. So output voltage is what? Output voltage is output current multiplied with RAC. Okay, and here we are seeing that this current IC, it makes the collector terminal negative with respect to ground. So we can write like this: minus HFE IB into RAC divided by the input voltage. Input voltage is IB into HIE. So it is equal to minus HFE into RAC divided by HIE. So it is equal to HFE RAC divided by HIE. Phase angle is 180 degree. This signifies, negative sign signifies that the phase angle between the input signal and the output signal is 180 degree. Okay, and what is HFE? HFE is beta. This is also equal to beta. Okay, equation for AB, it is equal to HFE into RAC divided by HIE. Phase angle is 180 degree. Then we can calculate the power gain. Power gain, it is equal to current gain multiplied with voltage gain. So we can multiply it like this. It is HFE multiplied with HFE into RAC divided by HIE. Okay, current gain and voltage gain multiplication. So it is the power gain. Then we have to determine the input impedance Zin. So it is equal to input voltage divided by input current. Okay, and AP, it is equal to AI into AV. So input voltage is what? Input voltage is IB multiplied with HIE divided by input current is IB. So it is equal to HIE. So Zin, it is equal to HIE. This is for approximate analysis. But if we are analyzing it for the complete circuit, then here it was earlier it was R1 and R2 was present. But in approximate analysis, because for this ideal source, if this voltage is ideal, okay, or for a good voltage source, its internal resistance is very less, then in that case we have approximated that since this resistance is very less and this resistance, the internal resistance of this voltage source, it is in parallel with R1 and R2, so under that case we have neglected this R1 and R2. But if we are considering this R1 and R2, then what will be Z in? It will be equal to HIE in parallel with R1 in parallel with R2. Okay, so we can write Z in, it is equal to HIE in parallel with R1 in parallel with R2. Now we have to determine the output impedance. Z out, it is equal to output voltage divided by output current. Okay. How we can determine the output impedance? Output impedance we can get it by using this formula, output voltage divided by output current. So for considering Z out, we are considering Vi is equal to 0, because for getting the value of Z out, we have to consider Vi is equal to 0. So if Vi is equal to 0, then what will happen? If Vi is 0, then Ib is equal to 0. If Ib is equal to 0, then this HFE into Ib, it is also equal to 0. Then this is Z out. Z out, it is equal to RAC. This is by using approximate analysis, but in true case, Z out, it is equal to RAC in parallel with 1 by HOE, because we have approximated it. It is 1 by HOE. Okay, because RAC, it is very less as compared to 1 by HOE, so we have approximated it. So in approximate analysis, we have removed this 1 by HOE. So but in exact analysis, Z output, it is equal to RAC in parallel with 1 by HOE. So we can write Z out, it is equal to RAC in parallel with 1 by HOE. So what we have determined, AI, it is equal to HFE, which is equal to beta. Voltage gain, it is equal to HFE into RAC divided by HIE, phase angle 180 degree. This can be also written as like this: HFE, it is beta, RAC divided by HIE, it is also equal to RI, phase angle is 180 degree. Okay, and power gain, it is equal to AI multiplied with voltage gain. Then Z in, it is equal to HIE in parallel with R1 in parallel with R2. It is approximately written as HIE or RI. Then Z out, we can write Z out, it is equal to RAC in parallel with HOE, RAC in parallel with 1 by HOE, so it is approximately equal to RAC. So in this way we can determine these quantities. This is current gain, this is voltage gain, this is power gain, this is input impedance, and this is output impedance of a single stage BJT transistor in common emitter mode. Okay. Similarly for common base and common collector, so we can determine all these quantities for this common base and for this common collector amplifier circuit also. Now we will see one example. This is the amplifier circuit. Okay, this is the amplifier circuit, and this BJT, it is in common emitter mode, and the biasing circuit, it is fixed bias. Here the bias is fixed bias. So for this we have to determine its AC equivalent circuit. We have to determine Zin, we have to determine AB, and we have to determine AI or current gain. How we can represent or how we can determine all these? So first is AC equivalent circuit. So how we can represent this? Its AC equivalent circuit. This is HFE IB, HIE, this is R1, and this is RAC, and this is the output, V out. Okay. So HFE is given as 100. So it is 100 IB. It is equal to 100 IB. HIE is given as 2 kilo ohm. So it is 2 kilo ohm. R1 is 150 kilo ohm. This is 150 kilo ohm. Okay, and it is grounded, and this is VI. Okay, so this is the AC equivalent circuit of this amplifier circuit. Okay, then we have to determine Zin. Zin, it is equal to HIE in parallel with this R1. So it is equal to HIE, that is 2 kilo ohm in parallel with 150 kilo ohm. So in this way we can determine Zin. Then voltage gain. How we can determine the voltage gain? Voltage gain, it is equal to beta RAC divided by RI. Phase angle is 180 degree. Beta, or it is HFE, RI it is HIE. Okay, so beta is given as 100, RAC it is given as RAC. We can calculate 5 kilo ohm. Why it is 5 kilo ohm? Because RAC it is equal to RC here, because RL is not present, so it is equal to 5 kilo ohm. Okay, now it is 5 kilo ohm divided by RI it is equal to to 2 kilo ohm. Phase angle is 180 degree. So in this way we can calculate the voltage gain. And how we can determine current gain? AI it is equal to HFE, and HFE is given as 100. So it is equal to 100, or directly we can write it is the output current. Output current is IC. It is equal to 100 IB. This is IC, and IB divided by IB. AI it is equal to output current divided by input current. Input current is IB. Output, this is IC divided by IB. It is equal to 100 IB divided, so it is equal to 100, which is equal to HFE. Okay. So now we can see that this is the circuit diagram of a BJT single stage amplifier circuit. And here the Basson is voltage divider Basson arrangement. Okay, so how to determine its AC equivalent circuit, and how to determine Q point, how to determine AI, and how to determine AV. Okay, so AC equivalent circuit, we have seen that for representing this AC equivalent, in AC equivalent we have to short this capacitor and we have to ground this VCC, and we have to replace this BJT with its H parameter model. Okay, so in this way we can represent its AC equivalent circuit. Then how we can determine AI? By using the same formula we can determine AI. We can determine AV by using the same formula. Then we can determine the Q point. Okay, Q point is IC and VCE. Okay, so in this way we can calculate all these quantities. Thank you.